Welcome to the pre-recording of lecture 24 of MCS 481. So this topic is on arrangements of lines, and we introduced and motivated the problem why we would be interested in arrangements of lines. Arrangements of lines occur in other areas, so I will start with an example in SageMath. So we will define the combinatorial complexity um, and then also give an incremental algorithm. Um, but let me first say if you want to see many examples, then you have a computer generating them. And there is the software SageMath. SageMath is free and open source for mathematical computations. It uses Python as its language, so it's quite straightforward to use. It's not only free and open source, it also runs in the cloud. So I'm running this on a Windows computer and on a Windows subsystem for Linux. In some sense, this is how I got into the Windows subsystem of Linux through SageMath. But if you do not want to install it, and we will not use SageMath much in this course, I just want to indicate it. The punchline is actually also here. Um, 2 or 3 lines of code and you see a line arrangement. It's called a hyperplane arrangement because it allows you also to define arrangements in 3-dimensional space. Okay, so here you see the 2-dimensional version. At first, the syntax might be a little bit off-putting, but that first line is very convenient to work with. So SageMath favors exact arithmetic. It's also a computer algebra system. We will work with the field of rational numbers, QQ, and we will define our equations of the lines symbolically. So I will swap immediately to the posted Jupyter notebook, but here is the plot that is shown. There are 4 lines. 2 of the lines agree with the coordinate axis. So y equals 0 is the horizontal coordinate axis, and x equals 0 is the vertical coordinate axis. Then we have 2 lines parallel to these coordinate axes. X equals 1, that's the vertical line, and then y equals 1 is the red line, so that's the line that we actually should look at first. Y equals 1 is that line parallel to the horizontal coordinate axis. So it's called box because you can see what it defines inside as its bounded region is a square. Okay, so let me now go to the Jupyter notebook. So I tried to make the Jupyter notebook self-contained, and there is much more that we can do than just looking at 4 lines in box. Let me go through this notebook. So I documented it. So we have the line arrangement, but in SageMath is a hyperplane arrangement. So the virtue of working symbolically with these letters x and y is that the equations x equals 0, y equals 0, x equal 1, y equal 1 can be defined very quickly, and here you see the plot. So 3 statements really, and we see a line arrangements. Now, what can we do with such a line arrangement? Well, we can query it, so I can ask for the number of regions. So if you look at the plot, we actually see that these 2 lines, they kind of partition the entire plane in 9 regions. So we have the box that is bounded, the bounded region, there's one bounded, but then we have the regions next to it, left and right, and then the 3 regions on top, 3 regions at the bottom. So we do have 9 regions in total. What else can we ask? We can ask for the bounded region. So here you see there's only one. So we get a tuple with one argument. We can ask for the defining equations. Again, these are hyperplanes. So hyperplanes is a method of our box, which is an instance of the hyperplane arrangement class. If you remember your object-oriented stuff. We can ask to compute the vertices. So there are 4 vertices, no surprise here. And then we can ask for the regions more specifically. So there are 9 regions. Here you see smack in the middle. So there is the convex hull defined by these 4 vertices. But then we have the unbounded vertices that are the unbounded regions that are defined by 1 or 2 vertices. So the one with 2 vertices are the ones that are the stripes at the left and the right and of the box, and strictly on top or at the bottom of the box. So we can verify that everything that Sage tells us is actually indeed what it is. Now, in this lecture, we will address the combinatorial complexity. We have only 4 vertices, and in some sense, if you want to be strict, mathematically speaking, we have a 5th vertex at infinity, which is at the intersection points of all the parallel lines. All right, we can generate many examples. So what does a random arrangement of lines actually looks like? Well, I tried first to work with random rational numbers, but I stopped doing that because it's a random rational number. Sage would often also return 0, and that's not my notion. If you generate a random rational number, then 0 should actually almost never occur. So instead, I will define a new environment, R, which works with letters capital X, capital Y, and over the real field of 53 bits of precision. So that means that corresponds to the double precision floating point numbers, also called the 64-bit float numbers. Here is how we can get a random element. In this sense, you will never get 0 unless if you're really unlucky. But here you now see 5 random hyperplanes, or I should say lines here. You can see how these are made. I made them with X and Y, the lowercase, and that's kind of a mistake from me, but it does not affect anything. So when I make the line arrangement, these hyperplanes are automatically cast inside the new R. Okay. So we have 5. 5 is a parameter here. I will post this Jupyter notebook if you like to see more or less. Just change the number. SageMath is strongly typed as well, so it allows you to work with exact arithmetic, rational arithmetic, or with floating point arithmetic. But you have to tell it explicitly what you want it to do. So that sometimes makes Sage a little bit difficult to use. So you see here what I just said about converting. I didn't think too much when I was doing these 5 random planes, so I was using the X and the Y, but as I'm making my line arrangement, so I'm actually doing a typecast, the sequence, so it's a list of hyperplane objects, kind of hybridly working with little letters x and y from the original field, but then the coefficients are random elements. But you can see that the little x and the little y get transformed in big Y's when you ask for the hyperplanes. The plot does not always look so nice. Actually, it looks so you can see that you can change this with the aspect ratio a little bit. I will not play with this, but actually I'm interested more in showing the number of vertices and the number of regions. Um, Unfortunately, and this is also the second reason why we have to be so aware of type conversions. Uh, the arrangements in SageMath are motivated by other areas. So there is a combinatorial way of looking at arrangements. There is combinatorial linear algebra. Matroids is one word that I saw in the errors coming up. Matroids is not an error, but it is a field that also uses arrangements. So just want to point this out. We will not talk about combinatorial linear algebra a lot or anymore, but this is where it occurs. So at this point, what I'm doing here, I'm converting the floating point coefficients into the rational arithmetic, into the exact rational forms. So this is where some persistence and expertise in SageMath plays off. But this is for the computations. So I'm now casting the hyperplanes in the original H, in the exact over the rational numbers. So I defined H over here right at the top. So this defines hyperplane arrangement over the rational numbers. So I started with the reals, with my random arrangement. I converted the coefficients into rational numbers. So here you see them. And then I took the list of uh, hyperplanes and I converted them into cast them into the H. And here you see then all the vertices. So in some sense, uh, this is not a course in symbolic computing or symbolic numeric computing, but we're doing symbolic numeric computing. You see the expressions coming up. It's not yet that bad because we are, in some sense, we're solving two equations and two unknowns, but you see that the random floating point numbers gave to very random coordinates and large coordinates in exact arithmetic. What is the point here? And that is important for what follows. If I'm keeping running this, and perhaps for the sake I should run this again. So I will run all cells. I should actually not rerun those. So let me start from here. So I have different random numbers. If I keep on rerunning this, so here you see a very nice, much nicer plot. So this is the plot. So let me now recompute the vertices. And then you see that the two numbers, 10 and 16, they changed the same. They did not change. They stayed the same. So that's an important experiment. So when we draw lines, um, if you think about the box, if you think about what I'm going to show the next exercise, they're not going to be as random. But if you consider random coefficients, you're always going to get the same number of vertices, the same number of regions. Okay. Um, I'm in 15 minutes, but we can generate many examples that way. So the first exercise invites you to play with this environment. If you have the disk space on your computer, installing SageMath is an investment, it's a good investment. If you have not used CoCalc, so here we see 4 lines, and this was this arrangement that pops in my head when I wanted to figure out an exercise, and you see that it's not as simple as it is. We will define simple in a minute. Here you see a vertex that is defined by 3 lines, not 2. So in some sense, these lines here, they appear kind of everywhere. So there are no parallel lines, but you see that you will have fewer vertices than expected. So the exercise is so you can, in some sense, count the number of vertices and faces. If you do not want to do this by hand, with software, you can solve this exercise by hand. You will still get um, more than half of the credit. This is an example that is not simple and where not all the lines are parallel. So that's also the virtue of this example here. Okay. Um, Examples and definitions. So here is the running example for what follows. 5 lines in the plane. I drew them to be kind of aesthetically well proportioned. So if you count, we have 10 vertices. The 10, it's 5 times 4 divided by 2. We have 25 edges. We will see a formula for that as well. And we have 16 faces. We can count them. Okay. Here now are the formal definitions. We are starting out with a set of n lines. So in every geometric problem, we have the dimension n. So here n is the number of lines in the plane. We have an arrangement of lines. When we talk about an arrangement, we have a subdivision. The subdivision consisting of the intersection points of the lines. We have the edges. So in the subdivision, a line actually gets subdivided. If the lines are general, so n lines will be cut n minus 1 times. So that's already a hint on how you can get to the general formula for the number of edges if you want to run ahead. We have faces. These are the regions, also using the SageMath terminology, the regions that are bounded by the edges. So they can be polyhedra or they can be polygons. Again, why are they convex? Well, every line defines a half plane. Intersection of half planes is convex. All right. We will in general work with simple arrangements. So the first examples on the slides here were actually not simple. So we had in the first exercise 3 lines passing through the same point. Using the terminology of the previous lecture where we saw duality, we have points that are collinear. 3 points on the same line corresponds through 3 lines in the dual passing through the same point. No 2 lines are parallel. So in some sense, a simple arrangement is defined by what it is not. So you do not have parallel lines and you do not have more than 2 lines passing through the same point. So we will work with those. Why? Because if we have parallel lines, we have fewer vertices. If we have also fewer faces, most likely fewer. So everything that is not simple will actually have fewer output in our subdivision. Okay, so here is then the first main result. The first statement here on the number of vertices, I already indicated with the 5 lines, 5 times 4 divided by 2. So there is also the number of edges, which can be at most n square. So every line is intersected by n minus 1 other lines. That's also to keep in mind. And we will prove also a bound on the number of faces. Now, if we have, so these bounds are sharp. So that's also what we experienced in the first calculations with SageMath. The numbers, I only did 2 runs, but if you are a little bit more suspicious, do hundreds of runs. You will see that if the random number generators are working fine, and with floating point numbers there should not be anything else, you will see that you always come up with the same numbers. And the numbers that you will find are actually here predefined by the results of this theorem. Okay, let's prove it. The number of vertices. So we have to, so you could see this proof as 2 statements, but actually we will prove that when the bound is not reached, then we don't have a simple arrangement. Either lines are parallel, or we do have lines that intersect in more a vertex where you have more than 2 lines. Okay, so the first count is combinatorics, n choose 2, or 2 choose n, choose 2 numbers out of n. So we have n choices for the first number, n minus 1 for the second, but we do not want to double count. So that's why we divide by 2. Okay. If we have n that many number of intersections, then we cannot have parallel lines, because if you have a parallel line, actually there's one point that vanishes. So if you have fewer number of intersections, then that could happen if you have parallel lines. But it also, and that's the other case where you can have fewer intersections, where you would have lines passing through the same point. A line is a line. I should actually say that you could say I draw 2 lines right on top of each other, but that's not a different line. So then actually your input is wrong. Then you have n minus 1 lines. I should have pointed that out as well. So the second statement in this count is by observing that the only 2 cases where you can have fewer than that number of intersections is when you have a thing that is not simple. Or otherwise said, that if the arrangement is simple, we have that many of intersections. Okay, second, the number of edges. So if we look at the number of edges, we have n square. How do we get to the n square? Every line is intersected by at most n minus 1 lines. So the number of edges on one line is at most n. And we have n lines, so we do n times n. So in some sense this was even simpler than the last time, because we can't double count. So we have n square edges. So if we have exactly n square edges, then actually every edge is actually intersected by exactly n minus 1 lines. And we have that it is simple. If we have a simple arrangement, no parallel lines, no more than no 3 lines that 3 or more lines that intersect in the same vertex. Okay, very well. We're almost done. The number of faces now. Well, we have an exact bound, and again, that bound is reached when the arrangement is simple. Okay, consider an incremental construction, and that is in some sense introducing the algorithm that we will consider in the third part of this lecture. So if we are adding the ith line, we will add I edges. So because we have already I minus 1 lines, and the ith line is therefore intersected I minus 1 times. So the ith line is partitioned in I edges. Okay, so how do we now get to a face? So every edge will actually split a face in two. Okay, so we started with one face. That face gets splitted in two, and then that other face also gets splitted in two, etc., etc. So the number of new faces that gets added is actually given here by this formula. So we have the total number of faces for which we find the exact geometric sum. Okay, everything is based on the number of edges here. So every edge splits a face in two if we add I edges in the ith step. Um, and actually, if we would have fewer than I edges, that could only happen when you would have parallel lines. And that again, in that case, we have a line arrangement that is not simple. Quod erat demonstrandum. So we are done with the first main result of this lecture. And actually, the result well, not the result of this lecture. In the next lecture, we will prove the zone theorem, which is another theoretical result. Okay, let's think about algorithms now. So here are the 5 lines again, but somehow you don't recognize them anymore. But let me point them out. So we have one line here, one line there, one line here, and one line there, and then we have this line. So you can see that there are still 5 lines, and there are 4 extra lines added with the bounding box. Okay, count the number of vertices, edges, and faces. So in some sense, this is also a line arrangement. So the box, so we started with a box. So we are going to combine the first line arrangement with the running example, the 5 lines. Does this actually change something to the theorem, to the results of the theorem? Count. So you can, if you like, you can also do this exercise with Sage. So if you want to do this fully automatic, you may have to do some coding because I don't think Sage uses a doubly connected edge list. But the Seagull does. So in the next lecture, I will point at how you can use Seagull from the C++ code. Okay. Here is now the connection with the line segment problem. So in some sense, we have worked with line segments already. In the pre-recording, the first pre-recording was a little bit confused and I pointed at the line segment, the arrangements of line segments. But if you would have scrolled down in the documentation, you would have seen also a picture for what I showed earlier. So you could say, look, as a mathematician, we have already solved this problem. Can we reduce the lines intersection problem to the line segment intersection problem. So mathematically, you could say, well, you just have to, you have to, you can probably do this. But before we start adjusting our code, let's think about the cost. Well, with the line segment intersection, that was the first time when we had an output sensitive algorithm. So the bound contained the number of intersections. So here the letter I. So we know that for a simple arrangement, and actually you could also say generic, um, if you use so the numbers do not satisfy any particular properties. They are completely independent from each other. Then actually we always have n square. So with the line segment algorithm, we also had this very quadratic bound, but line segments can be extremely short. So you can think about a street. We have very long boulevards, but after all, we have many alleys and many smaller streets that we and uh, any street intersects only with a finite number of other streets, even if your street plan has thousands of streets. Okay, if we are directly going to apply this output sensitive result, then we end at n squared times logarithm of n. And that is not optimal because n squared is the optimal result. So in some sense, we have a little bit the opposite reasoning of what we've done earlier in the course. We had an algorithm from the complexity, and then we dismissed that algorithm because it was not optimal. Here, actually, we have an algorithm that is already very good for the line segment intersection problem, but we can't use it. And instead, the straightforward way of computing all intersection points is actually very good because it applies to all simple line arrangements. So unless you work with specific applications, you can't do any better. So that is why we are going to compute all the intersection points first. Okay, and that is a pre-processing step that takes n square running times. Then we're going to add the lines one after the other and to construct the doubly connected edge list that will represent the subdivisions defined by the arrangement of lines. So step one should be clear. Also the running time, it's n square. The big O means that the 1/2 and doesn't really matter. So in some sense it's n times n minus 1 divided by 2. In practice, the 1/2 matters a lot, may matter a lot, but for asymptotic complexity, it does not. Okay, if we are interested in a good algorithm, then step 2 should actually not take more time than n square. So we are going to add the lines one after the other and update the doubly connected edge lists. How does this work? Here you see a picture. So we have an extra blue line coming in. Actually, the blue line, was it one of the 5 lines? Yes, it was one of the 5 lines that are colored in blue. But we imagine that this is the new line coming in. Then you see that certain faces are being split, edges are being split, and we have the vertices that we essentially have already computed. Okay. Adding a new line, we denote A sub I, the subdivision after adding the ith line. So if we have a new line, then we split the faces. So there is some sorting that we can do. So we have already computed all the intersection points. So if you have a new line, you can run over all these intersection points and filter out those intersection points that satisfy the equation. It's n square, but we have already spent n square. While you're doing this, you can sort them. So um, the number of vertices on the line will not be n square, so it's more likely that it will be of the order n. So we can, the sorting of these intersection points on the line, that's also certainly not n square. Um, Although ordering from left to right, you can do quadratic sort if you like. So it will be n square, but that's fine. So we have then on the line our points ordered from left to right. And that's the order in which we will process the points. We will walk on the line from left to right, hopping from vertex to vertex. So the number of steps is defined by the number of points, number of vertices on the outline. So we will enter a face through an edge, follow the pointers, and then get to the adjacent face. We enter a face and then we leave a face. Okay, how to find the leftmost edge intersected by, so perhaps I should actually, here is the picture. And I was too quick here. So the text is perhaps not so clear. It will come clear when we look at the picture. But here are the questions that we need to consider. If we are entering a face, how do we find the leftmost edge? And how do we split the faces? So the vertices are dealt with already, and they are ordered. And in some sense, the edges on the lines, um, so that's also taken care of. So I didn't spend too much time here, but if you go from the points from left to right, so you start at the left bounding box, or you could also say top to bottom. So, but you will, so here for simplicity, if you know the left to the right, then you can see all the edges that you need to add that are connecting vertex by vertex. All right. Um, So consider the face where the new line leaves through a vertex. How do we find the face adjacent? So in yellow, this is the face that we are leaving. How do we find the face that is adjacent to it? Perhaps not so obvious here because the adjacent face is over here and you don't want to end up over there. So in some sense we are intersecting. If you look at the twins, you may end up to two other uh, faces that actually are not adjacent. So there is some thought that needs to go into that. You have to consider all the edges that are incident to the vertex at where you leave the face. Okay, how do we find the leftmost edge of the um, edges? Well, you consider all the edges on the bounding box. Sometimes it's to the left, sometimes to the bottom, or sometimes starts at the bottom as well, at the top or bottom, depending on the slope of this line. And that could be an optimization. If you have a line, you can compute the slope and try to predict where you need to consider. But in any case, if you have to test all the edges, then that can be done in time proportional to the number of lines you have already processed. So here it says how many edges that there are on the boundary of the box. So finding the leftmost edge is linear. So how do we split a face? Well, we have the above and the below. We may have the left and to the right as well if you have a line that goes more vertically. But you have two sides in any way. So we split the edges where the line leaves the face. We know the vertex where we are leaving. So we will make new edges and also make sure that we have this doubly edge connection, so every edge has a twin. So this is where the half edges come in, and there is the pointers. We have the doubly connected edge list is not only the picture, but actually is defined by the tables, the vertex records, the edge records, and the face records. So every face is again a convex region. So the total time for the split is linear in the complexity of the face. Okay, that's almost it. So here we have the algorithm. We will get back to the algorithm in the next lecture and indicate its cost, its total cost. So we have to show that the cost does not exceed n square, where n is the total number of lines. So we have the pre-processing step where we are computing all the vertices. So this is step 1, all the vertices with the bounding box as well. We will update the doubly connected edge list. So there is the loop, the first loop, and then there is another loop that is inside of there. So the last step was proportional to the complexity of every face. So we have to be careful that we don't have somewhere a triple loop sitting in there. So we are going through the faces that are intersected by the line, and the number of faces that are intersected, I can actually give away the zone theorem already, is linear in n. So that is why the number of faces that we have to consider during this algorithm is linear. So we have an n square algorithm in the end. Okay, so this was a lot to take in. So we have seen that SageMath is actually quite convenient to generate many examples. So without us having to know too much about um, arrangements. We defined the combinatorial complexity of a simple arrangement that gives us an upper bound. So while we could have used an output sensitive algorithm, that didn't make really much sense if, say, for any random arrangement of lines, you have n square either. And it didn't make much sense because we would end up with n squared times logarithm of n. Okay, so I hope that this lecture makes things a little bit easier to read the textbook. In any case, consider the exercises 1, 2, 3 on the slides. They are intended to give you pause a little bit and to reflect a little bit on the concepts that we considered. Okay, so this is the central lecture of chapter 8 on arrangements of lines in the textbook. In the previous lecture, we motivated using computer graphics. In this lecture, we actually get a little bit to combinatorial linear algebra or matroids. In the next lecture, I will prove the complexity, the cost of this algorithm introducing via the proof of the zone theorem. And we will also look a little bit into Seagal again.